Hello everyone, my name is Oren Salzman and I'm an assistant professor at the Technion, the Israel Institute of Technology. And today I want to share my work on approximate bi-criteria search. To motivate this talk, let's take a virtual bike tour in the northern part of Israel where the Technion, my university, is located. Specifically, we're going to ride between Akko and the Sea of Galilee. Akko is a city on the Mediterranean, and the Sea of Galilee is a beautiful lake in the northern part of Israel. If we go to Google Maps and try to find directions between Akko, or Acre as it is called in the map, and the Sea of Galilee, we see three different options: top, bottom, and middle paths. And we can see that they differ in their travel time. If we would only care about travel time, clearly we would take the top path. However, since we're taking a bike tour, we also care about total elevation gain along the path. If we look at the total elevation gain, the top path, which is the shortest, has the highest total elevation gain. And the question is, which path do we want as a user, and which paths or set of paths should the system recommend to us? And informally speaking, this is the problem of bi-criteria shortest path, where we want to compute a path or a set of paths that somehow balance between, in this case, two possibly conflicting criteria. Now, this problem has a lot of applications beyond biking from one beach to the other. Two examples are planning of power transmission lines or transporting hazardous material in order to balance between minimizing travel distance and risk of exposure to these hazardous material for residents. Let's try to develop some technical machinery so we can formally talk about this problem. So in our motivating example, we had three paths: pi 1, pi 2, and pi 3, each with its own travel time and total elevation gain. And we can think of these paths as points on a two-dimensional plane. Here, the x-axis is going to be the travel time. The y-axis is going to be the total elevation gain. And a path is a point on this plane. And we want the path to be as close as possible to the origin. Namely, the smaller, the better on both the x and the y-axis. So we can plot pi 1 as some point in this plane. And when we compare pi 1 and pi 2, we see that pi 2, the bottom path, has a longer travel time, but the total elevation gain is smaller. This means that pi 2 is going to be to the right and to the bottom of pi 1. Now, if we look at pi 3, the middle path, it has both the longest travel time and the highest total elevation gain. So this path is going to be both to the top and to the right of both pi 1 and pi 2. Let's formalize this mini discussion. If we're given a graph and two cost functions in this graph, we say that some path to a specific vertex weakly dominates another path to that specific vertex if its cost is smaller or equal than the other path's cost given on both cost functions. Pictorially, we say that a path pi u weakly dominates all the paths that are to the top and right of that specific point. Given the notion of weak dominance, we can define the so-called Pareto-optimal frontier of a certain vertex. And this is simply the set of all paths connecting a start vertex to this vertex u, such that every other path from the start to u is weakly dominated by at least one path in the Pareto-optimal frontier. If we look at this pictorially, we have a set of paths, and if we take all paths such that for each one there's no path to the bottom left of it, we get the Pareto-optimal frontier. And we can easily see that all other paths are to the top and right of one of these paths in the Pareto-optimal frontier. So we would like to compute the Pareto-optimal path because these are the paths that in some sense are the best for some balance between the two optimization criteria. Unfortunately, computing the Pareto-optimal frontier is NP hard. Not only that, even determining whether a path belongs or does not belong to the Pareto-optimal frontier is already an NP hard problem. Now, existing algorithms to solve this bi-criteria shortest path problem either try to efficiently compute the Pareto-optimal frontier or try to relax the problem and only give some approximation of this set. Now, if we would like to efficiently compute the Pareto-optimal frontier, we're always going to be faced with a problem where the solution can be exponential in the size of the input. On the other hand, if we want to take an approximation approach, these are often slower in practice when we want to give some guarantees on the quality of the solution. And when running these algorithms on relatively medium or small size graphs, namely on the order of tens of thousands of nodes, these methods are often slower in practice than exact approaches. And very roughly speaking, this is because these algorithms typically partition the space of solutions into cells according to the approximation factor, and I'm going to formalize what this approximation factor means in a second. But this partition is done in advance, and this means that it has to be overly conservative. The key insight that motivates this work is that we're going to take an approximation scheme, but we can efficiently partition the space of solutions into cells during the algorithm's execution and not a priori. And this is quite technical, and I'm going to give you some flavor of our work and going to refer to the paper for more details. So again, we'll have to develop some common language so we can formally state what we're doing. And this is going to be done by extending the notion of weak dominance that we introduced several slides ago. So if you remember, we said that a path pi u dominates other paths to the same vertex if they're to the top and to the right on this pictorial representation. And we want to somehow relax this. So instead of asking that the cost is smaller or equal than the cost of all other paths, given some approximation factor, we're going to say that the cost is almost smaller than the cost of the other path, given both cost functions. Stated pictorially, we are allowing paths to be epsilon dominated, not only if they're to the top right of a given path, but if they're not too far away informally to the bottom or left of this specific path. Formally, if we're giving some approximation factor epsilon, we require that the cost is no more than 1 plus epsilon times the cost of the other path. And this holds for both cost functions. Just as we relaxed dominance to approximate dominance, we can relax the notion of Pareto-optimal frontier to approximate Pareto-optimal frontier. The approximate Pareto-optimal frontier is a subset of the Pareto-optimal frontier, such that every path to that specific node is epsilon dominated by a path in the approximate Pareto-optimal frontier. In this example, for the epsilon that I chose, we can approximate the Pareto-optimal frontier, which is the set of black dots here, using only two solutions, the one that I circled in purple. And this gives some intuitive flavor how we can avoid the exponential size in many practical applications of the Pareto-optimal frontier using a small approximation factor. Now we can finally formally define the bi-criteria approximate shortest path problem. Here we're given a graph, two cost function, and start and goal vertices. In addition, we're given some approximation factor epsilon. And the bi-criteria approximate shortest path problem calls for computing an approximate Pareto- optimal frontier. 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 Pareto- opti Very intuitively speaking, we would like to run an A*-like search and use the notion of approximate dominance to prune away paths. So just like in regular A* search, when we come to compare two paths, and if one dominates the other, we can prune away the other path, we would like to do something similar here. The question is, can we simply discard any path that is approximately dominated by a computed path? So to answer this question, let's look at this toy graph. We have here start vertex in green, goal vertex in red, and each edge has two cost values. In this specific example, we have three paths connecting the start and the goal. Pi1, which is the yellow path, Pi2, the purple path, and Pi3, the blue path. I plotted each one of these paths on our handy plane, and we can see that no one of these paths dominate any other. So all three paths are on the Pareto-optimal frontier to the goal vertex. Now, let's see what would have happened had we taken the approach of pruning away approximately dominated path. So in this setting, we're going to look what happens when we reach this intermediate vertex V3. In V3, we have both the yellow path Pi1 and the purple path Pi2. And in this setting, the purple path Pi2 approximately dominates the yellow path Pi1. So we can prune it away. Now let's say that the A* search continues and we reach the goal node. Now we have the blue path, which was already computed, and we compare it to the purple path, Pi2. And we can see that Pi2, the purple path, is approximately dominated by Pi3, the blue path. So we can throw it away. The problem is that Pi3, the blue path, does not approximately dominate Pi1, the yellow path. However, because it was discarded in previous search iterations, and we did not account for this, we lost a solution in the approximate Pareto-optimal frontier. So the take-home message from this part is that we somehow need a mechanism to account for pruned paths. So the key idea that we introduce is that a node will also store some information on all paths that were pruned in previous search iterations. The question is, how should we store these set of paths? And the way we're going to do it is using two representative paths, which we're going to call path pairs. So a path pair corresponds to 2 points on the Pareto-optimal frontier, and it represents all the solutions in the Pareto-optimal frontier between these 2 points. So in our example here, we have a path pair, Pi-u top left and Pi-u bottom right, and these are the extreme points of the path pair. And the path pair represents all solutions between these 2 points. We're going to say that a path pair is epsilon bounded for some approximation factor epsilon if all these intermediate paths between the extreme points are approximately bounded by both extreme points. Namely, every one of these intermediate solutions is approximately bounded both by Pi-u top left and by Pi-u bottom right. Now, we can describe in general details our algorithmic approach, and I want to refer you to the paper for further details because there are a lot of small details here. So what we're going to do is run an A*-like search. Instead of having nodes representing paths, as in similar A*-like algorithms, here nodes are going to be path pairs. When possible, we're going to merge path pairs. And this possible is only when the resultant path pair is going to be epsilon bounded. And this ensures that the solution is going to be epsilon bounded for every path pair. Now we're going to return all path pairs that reached the goal vertex And for each path pair, we're going to take one extreme point as a representative of all the solutions within the path pair. And I refer you to the paper for more details. To give a glimpse of the performance of this approach, we compared it with BOA star, which is a very recent algorithm that was shown to outperform the state-of-the-art in bicriteria shortest path by an order of magnitude, and sometimes by several orders of magnitude. When we compared our approach with BOA star on large road networks, having more than 1.5 million vertices, we get an average speedup of almost 8 for very small approximation factors, roughly 7. Interestingly, for small approximation factors, the extra machinery that we introduce makes our algorithm slower than BOA star. But for intermediate size, say 0.1, which corresponds to a 10% approximation factor, we already get a 5x speedup. For further details, I want to refer you to the paper, and I want to thank you very much.